by either of the two I showed you, or the internal coordinates and get the degrees of freedom what you really want. Okay, that's fine. What I did not really cover in the class is the suppose people only give you the molecule and do not tell you what is a point group. Okay, I presume that I think all of you have gone through enough exposure of group theory. I presume that I think most of you, even our BS students and our MSc students, have gone through in the earlier courses. But however, the tutorial is kind of, if someone has not, I think this is to bridge that gap. Okay, suppose I just give you a reaction in the class, I think, or in the exam, that I have a complex nickel tetracarbonyl and I react to the phosphine gas excess in say under ambient conditions. Okay, under ambient conditions, and assume that the reaction is not known before, I can generate a series of products. Nickel tetracarbonyl can lose only one of this carbon monoxide and a phosphine can come, or it can lose two of its and have two phosphines. A nickel can just retain one carbon monoxide and have three phosphines. Okay, or simply no reaction also take place. Okay, all these possibilities are there. Of course, the extreme reactivities, all of them gone as PS 4 times. Okay. Now assume that I think the reaction conditions have been monitored in such a way that there's only one of these products is formed, but you don't is formed. You can use a number of techniques, of course. IR is the best. I think metal carbonyl chemistry. I hope Pradeep Mathur has taught you. I think how powerful is infrared spectroscopy in following the reactions and characterizing products in metal carbonyl chemistry. One can of course use the NMR here and look at the phosphorus NMR, but it doesn't make a big difference whether one phosphine is connected to the metal, two phosphine or three phosphine connected to the metal. The chemical shifts will be 10, 20, not 10, 20. I mean 1 or 2 parts per million. This way, that way. Really, NMR cannot really help. Of course, you can get a crystal and do a structure. I told you that in the beginning of the course that X-ray is the most expensive technique in terms of machine time and efforts. So IR becomes extremely handy because each of these molecules, okay, have a different point group symmetry. Okay, so that essentially means that if you are only look at the carbon triple bond O stretching frequency, okay, you can easily characterize the product you have. You can find out whether it's a mixture of products, whether it's a single product. If it is a single product, which product is it? Is it a dicarbonyl or a tetracarbonyl or a tricarbonyl or monocarbonyl or complete argon? Because we know the IR region is about 2200 to 1900 for carbon monoxide. Depending on how many frequencies you have in this region, you can easily figure out what product. This is really the interpretative part of this spectroscopy. Okay, so if somebody just asks you that I have done a reaction of tungsten hexacarbonyl with a phosphine or pyridine and got a yellow product from a colorless solid, which is the starting compound, and how do you characterize this compound using IR spectroscopy? Or somebody gives you a spectrum and ask you to relate the spectrum to one of these 4 or 5 molecules. How do you do this?
Checking for typical markers for functional groups.
I'm sorry?
Checking for typical markers for functional groups.
Exactly. I mean, like that's one. See, but the thing is, the carbon monoxide, as I said, has 2240 or 2230 wave numbers as the stretching frequency. If I do some substitution, the phosphine will not have much effect on the stretching frequency itself because phosphine is as pi acidic as carbon monoxide. I think this is taught for you in 541, 547 in some other courses. Okay, they are of similar pi acidity. There will be an increased metal carbon bond order and decreased CO bond order, meaning the 2240 or 2230 wave numbers will fall to 2140 or 2150. but this is not going to be really marked. It is marked, but it's not significant. What is significant is the number of vibrational frequencies itself will change. That's where I think the group theory becomes important. I think the region will tell you if carbon monoxide is there or not. That's what the IR spectroscopy for organic chemistry would have been taught for you. Okay, you essentially look for signatures for N double bond N, C triple bond N, C triple bond O, C triple bond O, or a CC single bond or a CC double bond, nitriles, isonitriles. All these fingerprint regions have been taught for you. But how do you count the bands? How do you see the bands are strong or weak or broad or sharp, and relate this to structure of the molecule itself is what I just really want to do. I think I will do this in the classroom. I mean, I'm not, the regular class on Monday. I'm just only trying to tell you that any such exercise would involve, as a step one, the identification of possible point groups for all the products. I mean, that's what is important. So let me just quickly run through. I presume that I think this has been taught. I'm only just going to refresh your memory. Then really do some examples. I think we will do determination of point groups for some of the commonly encountered inorganic molecules. Okay, the next slide what I have here, I think the various symmetry elements have been spoken time and again. Okay, so you have a identity operation. You have reflections of plane. It could be vertical, horizontal, and dihedral. Okay, these are the three kinds of planes. I just show you quickly one slide for each. Inversion with an example. I'll show you for each one of this. And you have what is called a Cn, and also you have a Dn. Okay, Cn plus n. C2 is Dn. I think probably taught for you before, but show you an example. And then the improper axis is nothing but rotation followed by reflection. Okay, these are the symmetry elements which you will find in any molecule that is thrown at you. Okay, nothing is going to come out of this. So identity, reflections of the vertical, horizontal, and dihedral type, an inversion center, rotation only with the C type, sometimes D type. You have a molecule like benzene. You have a C6 axis, and you have 6 number of C2 axis. Then you call it as a D6. Okay, not as a C6. Then improper axis like one in ferrocene I showed you, or even methane. Methane has a okay, the methane with the 4 hydrogens has an inversion, not inversion, an improper axis, which is the S4 axis. Okay, the next few slides are going to just show you pictorially these symmetry operations, because once you know the operation, then you can build the point groups. Okay, so essentially here I taken a molecule. I think the one on the left is probably BF3, boron in the middle. Oh god. So I have boron in the middle, 3 fluorines here. So it has a C3 axis running through this through the boron, and you see each of the BF axis in the plane 1, 2, and 3. You have 3 C2 axis. So essentially you have a C3 axis and you have a 3 C2 axis. So this means you have a D3 symmetry. It is actually D3 symmetry means these C2s have to be perpendicular to the initial C3. Okay. Another beautiful example is benzene molecule. Benzene molecule is a C6 running through the center of the benzene ring from top to bottom. Okay, I don't know whether you can see my hand in the other computer. Okay.
We can't actually.
You can't really, just okay. So you have a benzene ring. I think you can imagine that. I think this is running through this the center of the benzene ring, and then you have a C2 here, a C2 here, and a C2 here, a C2 here, and a C2 here, and a C2 here. So essentially 1, 2, 3, 4, 5, 6. 6 prime, okay, 5 prime, 4 prime, 3 prime, 2 prime, 1 prime. Okay. So essentially you have a C6 axis plus 6 C2 axis, so it makes it as a D6 again. Okay. So this is a D3, a BF3, and this is D6. And here is an example of I'm sorry, you can just take this as a PTCl for 2 minus, PTCl, Cl, Cl, Cl. It's a planar molecule. You have a C4 axis running perpendicular to the molecular plane, C2s 1, 2, bisecting this and bisecting this. So you have a C4 plus 4C2. Okay, again it will be a D4. Okay, and there are molecules which have only the C axis but no D axis. That means the molecules do not have a perpendicular plane. We saw the examples in last class. Water having only C2, ammonia is having only C3. Okay, they do not have a corresponding perpendicular C2s. Okay, however, if I were to draw in this little space I have, the this is not okay. This is again a C2H. Okay, this is again a C2. Okay, and the cis form is a C2V, but both of them have a C2. Okay, this also a C2. The C2 is, it. This is the C2 for the trans, and for the cis, the C2 is like this. Okay, so both of them have a C2, C2H and C2V. So this is just a one slide, demonstration of the D axis. Okay, just move on. Okay, this is again just showing the various C2 axis along with the mirror planes. I think I skipped this slide because this comes again one more time. Okay, now no dihedral. No, God, I have one slide missing here. I think this is a vertical planes actually. Okay, so this is a C2 axis. This is one sigma V, and this is other sigma V. Okay, let's say this is XZ, and this is YZ. What is important is that when you say sigma V, that means that these two planes are along the direction of the principal axis. So sigma V means plane vertical along or coinciding with okay, principal axis. Okay, again here you can see that the sigma v's that are shown here, the sigma v here and the sigma v here and the sigma v prime here for the molecule PTCl for 2 minus are sigma v planes. Okay, however, there may be cases, okay, they are vertical parallel to principal axis but bisecting two C2 axes. Suppose if a plane bisects two C2 axes, then you don't simply call it a sigma v, you prefer calling it, or you should call it rather, as sigma d. Okay, for example, the plane what is shown here, this plane bisects this C2 prime and this C2 double 2 prime. Same way, this mirror that is shown here bisects two more C2 axis. So whenever a mirror plane which is vertical coinciding with the principal axis also bisects two other C2 axes, then these are called dihedral angle. And the third one is very easy to visualize. That is a horizontal plane sigma. So sigma v we saw, sigma d we saw, sigma h is nothing but the plane is always perpendicular to the principal axis. So if you have a perpendicular to the principal axis, you have this. So now we see in the bottom slide, sigma v is shown here, xenon tetrafluoride. This is the principal axis running through this, and this plane is sigma v. Okay, this plane is sigma d, and this plane, which is the plane of the paper, is sigma h. So xenon tetrafluoride has C4 axis, 4 C2s, sigma v, sigma h, and sigma d. I'm not adding up any of this. I'm just only telling you that you have to identify the symmetry elements in each of these molecules. So have you understood the three kinds of planes? Vertical, dihedral, they belong to the same type. Only thing is, vertical plane does not necessarily have to bisect two C2 axes, but the dihedral plane have to bisect two C2 axes. Okay, whereas the horizontal plane is a plane which is perpendicular to the axis of rotation. Okay, if this point is clear, let me just move on to go and show what is the next one. Okay, that is the inversion center. So this is the methane molecule, okay, which is in the staggered form. The staggered, okay, this hydrogen is coming out, this hydrogen is going in. So I can reflect or I can invert this hydrogen with respect to this point, the inversion center to that side, this here and this here. Okay, when you do an inversion, okay, one part of the molecule gets it was before inversion. Okay, a nice example of a ruthenium hexacarbonyl here. The inversion center is the metal itself. Each carbon monoxide gets inverted to the opposite side when I invert. Okay, a beautiful organic molecule, a butadiene, tetra difluoro dichloro tetrahydro no, cyclobutane. I'm sorry, one second. Let me just go back. Okay, you have a C4 ring, and I have 4 hydrogens, 2 here and 2 here. So this can get inverted here, this can get inverted here, and I have a fluorine here which can get inverted here, and I have a chlorine here which can get inverted here. The inversion center is right in the middle of this C4 ring. Okay, carbon, carbon, carbon. So I have 2 hydrogens up, 2 hydrogens down, 1 fluorine up, 1 fluorine down, 1 chlorine down, and 1 chlorine up. Okay, that's how this works. So inversion symmetry. I think the other example I showed you a while ago was the hydrogen peroxide inversion center. This oxygen goes here, this oxygen comes here, this hydrogen goes here, this hydrogen goes here. So this is a center of inversion. Okay, and improper rotation needs a bit more of imagination. It's not very difficult. This is methane. I showed methane in this slide in such a way that I can rotate it through 90 degrees. Okay, I can rotate this molecule methane to 90 degrees. Okay, so let's say that these two are in one plane along with this other atom, and these two are in a plane along with this atom. There are actually 2 planes. Okay, so if the 2 planes are perpendicular to each other, so when I rotate through 90 degrees, these two which are actually perpendicular to the plane of the iPad or the board now gets widened, which were far apart or wide apart to start with have come in the same, the plane along the perpendicular to the plane of the board. So this image and this image are not same. This is not a allowed operation in a group theory, because I told you blinking the eye. Okay, you blink the eye, somebody else does the operation. When you open your eyes, you see exactly what you saw before, although the molecule has been operated upon by a symmetry operation, but you see no difference. But here you will see that the top 2 hydrogens, which were actually seen as one because they are in the same plane to your eyes, now has become separated. The 2 separate hydrogens in the bottom have become in the same line. Okay, they have gone into the same line. So this is not really same. But however, if I do a C2 rotation and add it up with a sigma, okay, I am reflecting this molecule. I just don't stop. I just rotate and also just slice it. Rotate and slice it, slicing it along this plane. Now the top goes to bottom, the bottom goes to the top, the bottom goes to top here, and the top goes to bottom, and this molecule and this molecule are identical. So if I do a C2 plus sigma, I get improper rotation, which I denote by S. Okay, so this is an improper rotation. There are other molecules like I just showed you the ethane, which is staggered. This again as a C3 here, okay, and a mirror here. So this again as a S6. Okay, you have to do 6 times to come back to this. Okay, that's why it's right is the S6. Okay, so you have an improper rotation in molecules such as this. Okay. Okay. Let me this. No, not C2. C4 and C4 is a 90 degrees. C4 and C4. I'm sorry. C4 and sigma is S4. Okay. So I have this methane, one hydrogen here and one hydrogen here, which are in red. There are two hydrogens that are in blue. So I do C2. This is not identical, but I've done a mirror. This becomes identical. And I think you can keep on doing this. So you have a S4 in methane. This is that you'll skip. Okay. So I kind of now explained all the of all the symmetry elements. Where is this here? And then now adding up these elements will give you the point groups. If I have only one sigma plane and nothing else in the molecule, that has a CS symmetry, the least symmetry. If it has only one inversion center, nothing else is called CI. If you have only the principal axis of rotation and no mirror planes, like carbon monoxide, for example, okay, only a principal axis of rotation, but it's actually D, not C. Okay, just an example. Okay, and no mirror plane, that is actually a CN point group. C2V we saw here, where you have identity, n-fold axis, and sigma V. And then apart from sigma, you have a sigma H plane, then it becomes CNH. So if you have E, n-fold axis, n C2s, okay, n-fold, this is the principal axis, this is a perpendicular axis, one sigma H, n sigma V planes, and one SN, okay, then it becomes a D4, D infinity H. So you can go on, keep adding more and more symmetry elements. These are extremely complex. They have too many, symmetry elements. Okay, so I just show this tree. I think I bet all of you have seen this. Okay, scheme of assigning point groups of molecules and molecular ions. You start here and go through this tree. Okay, through various branches. You will essentially keep saying yes, no, yes, no, yes, no for each of the questions. Is molecule linear? Yes. Okay, then you forget the left hand side. Then is molecule has a center of inversion? Yes. Okay, D infinity H. Okay. What is the example here? Can you give an example here? Any one of you unmute and give an example?
Acetylene.
Acetylene. Right?
Yes, yes.
Okay. If the molecule has no inversion center, it's a CNV. Okay. So if the molecule is not linear, does a molecule have any of the isymmetry? Directly assign it. If it does not have it, then ask for CN axis is there. Yes. Does there a perpendicular CN axis? If there's yes, you go to D. If there's no, you go to C2H, CNV, and the just CN axis. And if the molecule has a perpendicular n times C2 axis, okay, and there is a sigma H plane, it's a D infinity H. If it does not have, you have a D and D, or just simply Dn. Okay, this is what you need to do if you want to solve problems which are having in an unknown point group. Some of the molecules you know by mind. Okay, you just have it in your head. You can just kind of say ammonia C3V. You can just say that BF3 D3H. Okay, nickel tetracarbonyl TD or WCO6OH. You can say this. But if there are some molecules which have, like the one what I showed you, cyclobutane with the 4 hydrogens, 2 chlorines, and 2 fluorines. I showed you only one of the conformation or one of the isomer. You can also have various possible isomers for this compound, and essentially have different point groups for various symmetries. Okay, various isomers rather. Okay, so I've just kind of taken an example here. I think what are we doing with the time wise? Only half an hour is done. Okay, we have good time. Okay, so I just taken the example of a PF5, and then again started substituting the fluorines by chlorine. Okay, and then taken SF4. There are 3 sets of molecules here. PF3 is like ammonia. There's nothing, but you can do a PF2 Cl PFCl2. Okay, other possible compounds, and try and assign point group for all these molecules, and then just look at the element fluorine stretching frequency, because we have an idea of where the element fluorine comes in IR spectrum in the in the entire centimeter inverse range. So you can really look at the fluorine ranges and see how many signals you are supposed to get for each of these. Okay, so you can find out which molecule you actually have. All of them have a PF bonds, but all of them will not have identical PF vibrational fingerprint. Okay, I mean the way it looks like, how many bands are shown. Okay, strong, weak. Okay, whether it's one-dimensional, band or in a A1 or A2 type or a E type or T type. All this information can be understood provided you actually assign point group for in each of these molecules and then derive the tau irreducible representations or the symmetries in terms of Mulliken symbols for each of the systems. Okay, so we will do for one series. I have shown one series here, another series here. I'm just substituting nickel, and a third series here. Okay, I think if you do this series, I think you probably would have mastered the art of assigning vibrational frequencies to their symmetries and predict the IR spectrum in terms of the pattern, if not in terms of the vibrational frequency numbers per se. Okay, because I for one do not believe in remembering too many numbers. Okay, but I think it's very important that you understand that even in NMR, it's important to understand the pattern rather than remembering is 1.23 ppm or 1.24 ppm. I think that's not really that much important. Okay, so when you do this exercise, you will at least know how does the spectral pattern look like. Okay, the reason I have chosen these examples than other example is that if time permits, towards the last class, I want to give you problems which combine IR plus 1H plus 13P, 31P plus 19F. Okay, a problem to solve by combination of these techniques. Okay, that's the whole idea of this course. Okay, because these molecules I can introduce. I will substitute in such a way that you have proton, you have fluorine, you have phosphorus, and you have switching frequencies. Okay, same thing can be done in carbonyl chemistry also. If my L is equal to a phosphine. Okay, so I can use here carbon monoxide, the IR spectroscopy. Here I can use a phosphorus NMR spectroscopy, and I can get a lot of information. And this gets more interesting when you go to these systems when L is equal to phosphine, because you have a cis trans for this, and you have facial meridional for this. So identification of this species becomes by combination of IR plus NMR becomes really interesting, and you can throw in some mass with this. I think you can even attack complex problems. So since it's a tutorial, I think now you guys have to speak. I think before I go on to do one series of these and wind up the tutorial in another maybe 45 minutes at the maximum, I want you people just to ask me some questions regarding whatever has been told now, because this is a tutorial, not a class. Okay, please.
So I had one question. So how are we correlating the symmetry groups with the IR spectroscopy? That part I didn't really get much.
How are we correlating is the question, is it?
Yeah. So suppose if I have a point group of a particular complex, so what will it be correlation in the IR spectra, so to say? Did we discuss that?
No, we will discuss this towards the end only. I'm not trying. See, let me just explain the sequence of events.
Okay,
We are talking chemical reaction. Okay, I'm just when does you use spectroscopy? When you use spectroscopy because you have performed a reaction, you have got a product, and you want to identify the product. Okay, supposing the reaction is an unknown reaction, you have not done this reaction before. It's not there in the literature. Nobody has reported this. Okay, you are going to use a series of techniques. IR is one such technique. Okay, what information IR can give? I think as somebody else just some time back unmuted and told, IR spectroscopy will give a fingerprint. Fingerprint of functional groups, right? So suppose I'm doing a reaction of a element halide start with, and introduce a element carbon monoxide, or the vice versa. I start with the carbon monoxide nickel tetracarbonyl and introduce a fluorine. I can either follow the carbonyl region of the IR spectrum or the halide region of the IR spectrum. Okay, and look for the starting material vis-a-vis or versus the product. Okay, what is the difference? Does this difference really corresponds to the expected products what I'm having in my mind? That's why you correlate it. Okay, the correlation comes from the chemical knowledge that I think these are the possible products. To which of these products this spectrum what I'm getting really would correspond, and there is a tie. You are not able to really assign whether this or that. Then you take a paper and pencil. Okay, apart you have a spectrum in the hand, you have a compound in the flask, and you have a paper and pencil. Now you scribble down the various products that are possible. For example, what you see in the screen, I'm doing a reaction of nickel tetracarbonyl. Okay, and I'm reacting phosphine in a solvent at let's say 40 degrees centigrade. Okay, I call this the A and call this as a B. Either I can form A or I can form B or I can form both. So without even using any group theory, okay, I can just tell you that because see, this is a beautiful molecule because I can study the nickel to carbon vibration. Unless I have no other job, I will not do that. Okay, or I'm sorry, you can study the only the CO stretching frequency, or I can study this bending vibration. I can study number of, because as I told you, this is 8 plus 1 9 atoms, 27 degrees of freedom, minus 6 21 vibrations are there in this following molecule. But why I complicate my life so much to understand the whole spectrum? I can only look at the carbon monoxide stretching frequency, right? So essentially my problem gets shortened to 4 vectors. I can rewrite the molecule only this way, right? And I know that this molecule is in a very high symmetry, is called TD. I know what are the symmetry elements for this TD because I have a character table printed in a book or in web page or somewhere. Okay, I know the symmetry elements E, C4, C3, S4, sigma, V. So many are there, and I have the corresponding. You have also in you don't know universal center here. Okay, so the A's and B's. Now, without worrying about the 9 into 3, 27 Cartesian coordinates, either through the Cartesian coordinates or through the sum of unmoved atoms plus the matrix traces, I can simply set up a tau CO. That's it. That's all I want to study, because I don't want to study too much of, I don't need information regarding the MC stretch, nickel C stretch, or a NiCO bending. Why am I really worried about this bending right now? I'm really not. So I will only worry about the NiC triple bond O frequency. So essentially, I only set up that and get A, B, C, D, E, F numbers. And I have the symmetry elements here, E, C2, C4, C3, etc. And then I can, and then their coefficients. I have the character table. So the character table, let's say I'm just putting as a A1, 1 on 1. Multiply this with this with this. Okay. And then divided by 1 over H, and the sum of the thing, and I get number of each of the vibrations. So I will find out that nickel tetracarbonyl has not too many vibrations. I'm not, unraveling the plot right now. I want to do this a little later in the class for everyone. Okay, you understood now, Harsh, what I'm trying to say? So essentially, this is how you will correlate. What I'm teaching is just to get an overall picture of what is going on in a molecule, but you don't have to necessarily exercise everything what you have learned when you are actually in the lab and trying to characterize a product. You will only use, that bit of information to, uh, unravel. Okay, how many CO frequencies are there? Because the CO frequency I go to an empty slide. Is this is my spectrum? Let's say this is 4000. Somewhere this is 2200, and this is my 1800, and this goes all the way to 400. Everything happens in this box. Okay, everything. Whether I just simply have one for tungsten hexacarbonyl, or I have two, I have three, or one broad one which is actually not resolved. So this, I'm sorry, what happened? This pattern is my actual signature. That is what is going to tell me whether my compound is a tricarbonyl or a dicarbonyl, NaCO3 or CO2, or even tetracarbonyl. Or if you go to the tungsten tetracarbonyl L2, it will not only tell me whether it is L2 or L3, okay, or WCO for L3, it will also tell me whether this is cis or trans. So here I will be only doing the 2 point groups for these two molecules. Let's take for this, for example, very easy. One is a C2V, other one is a C3V for WCO4L2. Okay, so essentially I do a tau R reduced using CO bonds for both these point groups and derive the number of frequencies. And I have probably just for namesake, just say that I have one, I have 4, and I have 3. Numbers may be right, may not be right. I come back and see whether I have 4 bands or 3 bands. I also know that I think where they should appear roughly, because symmetric versus asymmetric, the force constants and the reduced mass. Okay, which is high energy vibration, which is a low energy vibration. So with all this information, I can tell you that I have a tri-substitution or a disubstitution, whether I have a cis isomer or a trans isomer. I think I probably have, I hopefully, rather not probably, hopefully I have explained what your question of at the end of the day, how do you correlate what I do on the piece of paper to the actual spectrum which I get out of the spectrometer. Is that right?
Yeah, I think this is the most fascinating part of this subject. Yeah.
Yeah. Anybody else?
So I think that's a typo you did, right? So it's WCO3 and L3, right? In the top right corner.
Yeah, that's just. I do a lot of such mistakes when I write. Okay, yeah. Like the SI symmetries become symmetries or something like that. Yes, in some ways. Okay. Uh, has that problem been fixed actually? The assignment submission?
Yeah, I think Gaji
Yes,
fixed
sir.
it.
Yeah, because I can evaluate right on the MS Teams, then the marks get added at the end of the day. Otherwise, somebody has to tabulate. Tabulation can create one wrong entry by missing one number in between. Everybody gets messed up. Okay, so better that I think everything is uploaded in the Teams only. Okay, so that my TS also don't have to just cross verify too many times. Okay, just let's move on now, and you tell me what I should teach next. I think based on this. Yesterday's 2 classes and today's the first half of the tutorial. What do you want me to explain?
So the internal coordinate parts are something
Okay,
very
that's all
new
right.
for most.
It's beautiful. Okay, then we will take an example of uh, what will we take? I think because I want to do something else in the classroom tomorrow is C2H versus C2V for. Okay, I will do. Hopefully that will be available for others. Then I go for SF4 tomorrow. Okay, so let me just take a white slate. Let's write 2 molecules here. I have not done this before. I may make mistakes. Okay, I'm just going to do this along with you. Yes, I have not prepared anything for this. I'm writing the 2 isomers of hydrogen peroxide. Okay, you know that this bond is very fractional. If I have, just hold on for a minute. Okay. 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 You can see this. Oh, the background. I am there. You can see this molecule, right? Assume this is hydrogen peroxide. Okay, right? So
Yes.
this bond is a fractional bond. You can pin my screen into your full screen so that you can see this better. Okay, so maybe I should put the same color here. Just hold on for a minute. So this is the two isomers I'm talking about. This is the cis isomer. The background is bad here. Now you can see this. I can rotate about this axis and then bring it to trans, right? So this is a trans. This is a torsion. Okay, I can bring it to here, then it becomes cis. In the cis isomer, the two-fold axis runs here. The white. Okay, this is a two-fold axis. Okay, and in the trans isomer, the two-fold axis is perpendicular to this bond. Okay, this is the two-fold axis. This is the two-fold axis. Okay, so the both the molecules have, uh, one is a C2V.
Professor, I'm sorry. Are you showing something?
No, I'm just writing now.
Okay.
Just hold on for a minute. No, I think I just take this phone call for a minute. Okay, just.
Yeah, sure.